His research work has been recognized by several awards, including the IISC Technical Innovation Award and Informs Impact Prize. Dr. Ding is the editor-in-chief of the Informs Journal on Data Science and has served as well as the editor-in-chief of IISC Transaction. So, Professor Ding, thank you very much for participating, and the floor is yours.
Well, thank you very much, Alan. I know it's a Friday afternoon, and thank you very much for coming to this tutorial. First, a little bit about logistics. So I plan to roughly stop at the top of the hour around like 4 o'clock and probably have a 5 minutes of break, and then to come back. We try to finish, as much as on time. Before the 5 o'clock. So you're welcome to interrupt, during the presentation. If you have questions, I think, more engagement and discussions probably make the presentation more interesting. Okay, so today, the tutorial I plan to do is talk about the data science method used in the performance quantification for wind turbine generators. We did this work for a span about at least 10 years, and our first paper published roughly about 11 years ago, but the work actually started even 3 years prior to that. And in 2022, Informs gave our team the impact prize. So sometimes people ask me, what we did to get that recognition, and here, let me to give you the full account of the type of work we did, right? Before we get to the technical work, I just want to provide a little bit kind of background and how does the wind turbine work. The wind turbine actually looks pretty simple from outside, right? You see a wind turbine, you see a tower, you see the blade, and then you see a kind of a box behind that, and include pretty much everything. If you click on this title, afterwards I'm going to provide a slide. So if you click on the title, it brings you to a website which illustrates the working mechanism on a high level, right? So if you click on next, here it tells this is explain the wind direction. It points to the blade and rotor, this is a main rotor, and low speed shaft, because the rotor rotates pretty slow, roughly about 16 RPM rounds per minute. And in order to generate electricity, either you need to have very strong permanent magnetic field to hold that the generator, or you speed it up, use a gearbox. So here you have a gearbox which is speed up the speed of the high speed shaft, which usually goes to over 1,000 RPM. And the purple cylinder is the generator connected with substation and so forth. Anemometer measures wind speed. Most of the anemometer, right now, all the practical anemometer is really after the rotor, right? It's not before the rotor. It actually has a practical implication because it's in the wake, which we're going to explain what is the wake effect of the wind turbine generation. There's a controller. There's primarily two major control mechanism on the wind turbine. One is called pitch control. This is a pitch system to change the blade rotation. And another is the yaw control, which is to change the pointing of the wind turbine. And then previously here, there's a wind vane, is measure the direction, and they do have a mechanical brake. So when the wind turbine need to be locked down, which doesn't really turn anymore, they apply the mechanical brake. Okay, and there's a yaw motor and there's a tower. So that's primarily the wind turbine at a glance, right? So if we go back to the slides here, that more or less give you some feeling. There's other control mechanism inside the turbine. like inside the nacelle, like the rotor regulator, so forth. So, but if you see the movement of the wind turbine, primarily there's a pitch control and the yaw control, right? So the wind energy, the same as the solar energy, are known as variable renewable energy. There's two keywords here. One is a variable, another is renewable, right? We understand it's renewable because the wind and the sunshine is always going to be there. And it's a variable because the fuel input, right? Wind energy is a wind and solar energy is sunshine. It's not really controllable. They're kind of being controlled by the natural environment. Not only the main force to generate the energy is not controllable, the other environmental conditions also affect the wind power generation. It's not controllable either. A commonly used so-called production function is called wind power curve function. It's showed on this side of the slide, right? This is really a nominal, very ideal wind power function. It's very clean, very thin, very smooth, and it connected the wind speed with the power production, right? The VCI is the so-called cut-in wind speed. Usually only about that wind speed, the wind turbine start rotating. And then VR is the so-called rated wind speed. And around that, when the wind speed approaching to that point, the pitch control start kicking in to change the wind blade to be more parallel of the wind direction, reduce the absorbability of the wind energy to be converted to electricity energy. So basically capture the wind power production at the so-called maximum capacity. People also call it rated power. And the VCO is the cut-out wind speed. So by the cut-out wind speed, the wind speed is considered too strong, could mechanically damage the wind turbine device. So the turbine is shut down mechanically, right? For a typical commercial wind turbine, VCI is about 3.5 meters per second. VR is around like 12 meters per second, and VCO is 25 meters per second. You probably don't really have a real sense of 25 meters per second because when we hear the weather forecast, the people don't really tell us, how fast is the wind speed in terms of meter per second. 25 meters per second is about 60 miles per hour, right? If you recall, the category 1 hurricane force is about 75 miles per hour. So it's slightly below that. And it's a pretty strong wind by 25 meters per second. Okay. So in the wind performance, in wind turbine performance, there's a lot of this kind of issues need to be analyzed, assessed, and quantified. And because the people come to realize, in operating in a relatively harsh environment outside doors, and the wind turbine actually deteriorate faster than the other kind of turbine machinery, right? Because the turbine has been in service not for very long. So if you look about 20, 25 years, the data, there's not really that many studies yet. But one of the study published in 2014, which I kind of, this is not our original data, but it's more kind of capture the overall trend. You can realize different from this kind of bathtub type of reliability curve. Here, they only have a very short period of a stable operation period from first 5 years also. Initially there's a kind of burn-in process. And then after that point, you can see a very clear degradation in terms of turbine performance. Now, it's not really very easy for you simply just say, let's replace the turbine with a new one, right? Because you install a turbine and buy one, it really costs a lot of money, right? People said usually it's $1 per watts, right? It's 1 million watts turbine is $1 million. And installing that takes another $1 per watt. So by 5 years, it's way too soon for you to replace the turbine. And what are you going to do, right? There's a lot of service provider to approach the owner operator to say, I have some kind of turbine upgrade, or I have a retrofit. I can add something on your blade. I can do certain things with your control, and therefore we can, restore your turbine production performance, right? It doesn't really come as a free, right? It actually going to cost the owner and operator. There's one of the questions is, does the type of service, does the cost to have this kind of service and really justify the service in the first place, right? I mean, does the revenue bring out by the service that justify the service in the first place? One of the example is the so-called vertex generator, right? If you look at the right-hand side of the slides, there's a blade as on the very first one is the vertex generator. So here's one example about the vertex generator. This is a piece of plastic. We worked with one of the small company in Germany, which produce this kind of design and produce this kind of vertex generator. And so the size of the vertex generator is roughly about the hand, the size. And on the bottom part of the vertex generator is really a piece of occlusive. So you take the plastic off, you can put that vertex generator on the blade. And the theory says all these kind of spikes will produce some kind of local small micro turbulence, and that will improve the so-called lifting characteristic. And with that one, you actually can improve the power production efficiency. Even the blade is not really of the optimal shape after a number of years service, right? When people did the experiment many years ago, almost 25 years ago, in the lab, they said the improvement it could be as much as like 25%, right? If it's indeed 25%, that's huge, right? In reality, it's not going to be that significant, right? There's a cost to install the vertex generator. As one of the picture you can see, people need to kind of climb to the turbine. They need to shut down the turbine. Not only this particular turbine, they need to shut down the nearby turbine for the safety of the service worker. The generator itself is not really expensive because the material is not really that much, and they can mass produce this kind of, once the design is there, they can mass produce. But the installation is going to cost quite a bit of money. And roughly speaking, about $10,000 per turbine. So if you have wind farm about 200 turbines, it's going to cost you $2 million. And typically, the owner operator needed to finance that cost. So they don't really kind of put all the cash over there to do the installation. So you add all this kind of finance, everything is going to be more than $2 million, right? The key question for anyone, whether or not they want to use this kind of service, is really, how soon we can get the money back by, newly produced actual energy, which the old turbine doesn't produce. In this slide for the 3D, the EDF together with the 3M, the 3M involved is really because of the adhesive. They actually produce that adhesive, industrial strength adhesive to put on the turbine blade. They claim they can increase AEP, annual energy production, 1.3 by 3%. You think that is a pretty small amount, but it's quite significant in terms of the revenue generated, right? If you can produce 1.5 to 3%, you actually can pay back this $2 million investment in about 1 to 2 years, right? We did a simple calculation. It is indeed like that, right? The 200 wind turbine 2 megawatts class 3% AEP generate $1.2 million revenue increase. This is assume the electricity is sold at 6 cents per kilowatt hour price, right? If the price is higher, you can get more revenue back, right? The 2 years is a $2.4 million. That's pretty much pay back the principal together with the interest, right? And this is not only this 1.5 to 3% is pretty realistic type of things, and the practitioner looking for, right? Through the studies and the collaborations with the industry, we realize not only VG installation, but some other the so-called turbine upgrade. Typically, they will provide 1 to 5% increase in AEP. Anything bigger than that, you don't really need much convincing. Industry already did that, right? Because the effect is so obvious, and people is not going to pass that on. And anything in that range is like we are not really sure, is this really kind of real benefit, or is really a noise? So because of the input is not controllable, it's not easy to do experiment for that, right? So detecting the small improvement, yet is still significant in terms of the revenue and the investment decision. and also attribute the effect to the very action you are taking, right? And it's a pretty important things the data science can contribute to, and in fact help them to solve this question. The performance quantification is not only relevant to wind industry. If you agree with me, I hope you do. For industrial engineering, the quantification is one of the very critical fundamental questions, right? We need to do detection, we need to do decision making, we need to do control other things. The first thing is really measurement and quantification. You cannot control what you cannot measure, right? The performance is one of the part. You have to measure the performance. You have to be able to compare, quantify, and eventually you know you are doing better or you're doing worse, whether or not you have actual quantifiable economic benefit. So this is really a question applied to a lot of engineering systems. Here, the things is difficult is because of the input is not really controllable. We'll come back to that point later. So in 2019, I published this book, and by the way, the ebook is free, so you can click on that the link and you can download the entire PDF, right? And in this book, we had one overarching formulation in this using the probability density function and the conditional probability density function, and that's structured in 3 parts. The first part is really talk about how do you model the P of X, the probability of the X. X is really the environmental aspect. So this is a wind field modeling, right? And that impact on the wind power forecasting. The second part is try to model the probability of Y as a power condition on X. This is related to the wind turbine. For a given wind speed, how much power you can produce. There's an uncertainty aspect, therefore it's a probability of Y, right? And then the third part is, suppose your output is not really the power production anymore, it's really the mechanical load, is the stress on the turbine, so we call it the Z. The probability of Z condition on X is given this kind of external force, the wind force, and what kind of stress distribution is going to be on your blade and on your turbine. And that is related to the reliability analysis. So this particular part, especially the Professor Bian from University of Michigan did a lot of work and published the important papers, not only talk about the physical load distribution, also the type of things coming from the computer simulation. Today we call it digital twin, right? How you're going to analyze this type of reliability data and collect the reliability data. But today, what I'm going to talk about related to that effort we did for the performance analysis is really related to the part 2 of the book, right? The part 2 is really try to model the probability of Y condition on X. And we actually established a pipeline which try to answer 3 questions. The first question, of course, is a very common machine learning type of question: which variable you're going to use? Subset selection, right? We have a bunch of input, and then you want to connect with the output of the power production, and which input really kind of matters. The second one is also related to this very much this variable situation. You cannot really use all the data as is because they're going to make your input output is less comparable. I mean, the before and after action less comparable. So there's question about which data set you're going to use. This related to the so-called causal inference type of literature. The last one, as everything we do in industrial engineering, applied statistics, we like to quantify the uncertainty, not only quantify the effect of upgrade, but also uncertainty that very assessment. And we were able to build the pipeline in both R and Python package. Later on, I'm going to show a kind of screenshot to say, we give you example, you can follow the procedure and use the example data set and go through each step yourself. Now, people said, if this is such an important question, why don't we just run a field experiment, right? The very reason, the simple reason is simply that field experiment cannot be done, okay? Because the size matters. And in this case, in order to run a field experiment to control the environmental condition, you need a wind tunnel. which is a wind tunnel. They probably need an AC controlled wind tunnel, right? The AC control need to control everything in that environment, but also the wind tunnel will control the wind condition, the wind speed and turbulence, whatever the things, right? So what kind of wind tunnel really we typically use? It's typically about the diameter of 3 meters. Okay, that's pretty large wind tunnel. You know, the smaller wind tunnel is like less than 1 meter, right? There are some specialized wind tunnel being used for primarily military service purpose. Maybe it can go up to 10 meters when they try to build some kind of new aircraft, everything they need to use that. There's not really that many commercially available, right? But even 10 meters wind tunnel compared with the wind turbine is still pretty small, right? Here I draw this picture. This is a very typical 2 megawatts class wind turbine, and the hub height, you know, is about 80 to 100 meters tall. The blade is about 50 to 60 meters long, right? And if you scale a 3-meter wind tunnel and you look at this little guy to your left, that's the wind tunnel, right? How you can press that whole thing into that tunnel? You couldn't, right? So many years ago, when people were doing this field experiment in their lab, and they said that the VG installation can give you 25% improvement, they actually did it on a very small scale, less than 1 meter, right? On that one, and now how you're going to go from that 1 meter to 50, 65 meter, and you do extrapolation. So you needed to do some kind of approximation, one way or another, right? From 1 meter to 65 meters is pretty large extrapolation, right? And no wonder that 25% promise never really materialized. Okay, so another thing you actually can do on the actual wind turbine is a so-called A/B test, right? They are not really called A/B tests in wind energy, but it's really the A/B test is commonly known nowadays because of they are using on the internet, right? But you can do something of this nature. There's a limitation to that, right? So how do you do the A/B test? First thing is whatever you test, that something being tested need to be able to switch on and off instantaneously. Okay, suppose a control logic can be switched to control logic A and control logic B instantaneously. So you can run the control logic A for 1 minute, and now you can run control logic B for another minute, right? And now you have this 2 consecutive time period. You simply take your time, the power produced in first minute and second minute, and you take a difference between these two. You just keep running these pairs and for like a considerable amount of time. For example, couple of months or a year, right? And then this total difference will speak to the difference between these two logic. The basic assumption to say whatever the wind condition and also the environmental condition between the first minute and second minute doesn't really substantially different from each other, which is a pretty fair assumption to use. Now, the reason this one is not really widely used is very simple, right? Because most of the type of the wind turbine upgrade need a physical action. You can not simply just switch on and off instantaneously. If you put the VG installator, the vertex installator on the blade, that takes time. That takes more than a day. Okay, and it's not easy just for you to take them off and then put them back on, right? So this is anything related to the physical action, right? Even something doesn't really related to the physical action, only related to the control logic or the software things. Sometimes also takes more than that. You do software upgrade, it takes more than 1 minute. And then you needed to do a bunch of other things to make sure everything kind of checked in, and then you can run this new software platform. And they don't really have that appetite to kind of switch that back on to go through the whole thing again. So this is very limited. They do use that sometimes, but not a whole lot, right? So we're still back to this question of the power curve. So the power curve is still being used as a primary tools to do the function, the performance quantification part. Right, from our mathematical model, the power curve actually is a conditional probability density. The one used in industry is really a function, is a one simple curve, right? So you deteriorate or you simplify from that probability from multivariate to a single variate, right? The first thing is like if the probability will deteriorate to expectation is still multivariate if the X include a set of environmental variables, right? The wind speed included. But if you reduce the X to only wind speed alone, the expectation of Y condition of Y is the univariate power curve. And we typically come across from the literature from industry use, right? And how does the industry use estimate their power curve? There's a time evolvement, right? 20, 30 years ago, there was a parametric power curve. They simply just say because the power production law says the power is related to the wind speed in this cubic law, right? The rho here is the air density. The A is the area of the rotor sweeping area. CP is so-called power coefficient. So on surface, this simple law says the wind power produced equal to something constant multiplied with 3. It's just that something multiplied is not constant. The CP is not constant. CP is also a function of wind speed. It's just the function form people don't really know. Okay, so in the end, the power is not exactly a function form of the wind speed. And it's not exactly the cubic function form of the wind speed. So the IEC 61400-12, which was enacted 2005 to give this so-called binning method. The binning method is a nickname we give to this method. And it's fundamentally a non-parametric method, which is very robust and very adaptive, and it's a data-driven, right? You don't really need to assume any kind of function form. The ideal is simple, right? You start from the cut-in speed to the cut-out speed. For this particular turbine, the cut-out speed is 20 meters per second. This is one of the old wind turbine we come across. And then from there, you cut the wind speed into small intervals. And the standard or the default value is 0.5 meters per second, right? And then you see how many this data point fall into different kind of bins. You average all the data point and you generate this kind of constant. And so the average per bin is considered the wind power produced for that particular wind speed bin. And you have a set of like 20 to 25 dots, and you use a smooth curve to connect them together. And that's the binning method. Okay. The IEC also recognized, right, from this power production law, the power not only being affected by the wind speed, but also affected by air density. And so they recommend use something called air density correction. So the air density correction is, use the sea level dry air density, which is constant, right, as a reference. And using whatever you measure for that particular location, the wind farm is located as the input value, and calculate this adjustment constant, multiply the measured wind speed, get a V prime. V prime is a corrected wind speed. And then the rest of things is the same. Instead of having a wind power between Y and V, you simply just produce a wind power curve between Y and V prime. So that's is incorporating the air density correction term. Another issue is about the wind direction, right? The IEC standard doesn't really advocate use the entire set of the wind speed through the 360-degree wind direction. The reason is, like I mentioned, this wake effect, right? Previously, when I explained how the turbine works, I said that the anemometer is in a wake, right? That's true for every turbine. But if you look at the pair of turbines, and given the wind directions, and it could put the downstream wind turbine in the wake of the first turbine, right? In the picture showing here, the turbine 2 is in the wake of the turbine 1. What it means is really the block of air pass through turbine 1. And once it pass through the turbine 1 only absorb part of the energy from that block of air. So the block of air still have energy residual in it. It still keep moving and hit the turbine 2. But when they go from turbine 1 to turbine 2, they've been disturbed by the rotation of the turbine 1. Number one, the amount of energy in that air block becomes smaller. Number two, they are not really kind of free movement anymore. They are kind of being more turbulent, right? There's this turbulence existence actually reduce the production efficiency for turbine 2. And when these kind of things happen, we said turbine 2 is in the wake of turbine 1. And there's a wake sector, right? Depending on the wind directions, there's a wake sector of the turbine 2. And for IEC standard, and they said if you want to have more accurate quantification of the wind power curve, you're not supposed to use the data in the wake sector. You should use it in the so-called free sector. The problem is, if you have a lot of turbine kind of near to each other, there's not really much free sector, right? Here is one set of the data to the right that we collected. The one with all these kind of black dots, those are the free sector. The data has been eliminated with the white space is the wake sector, right? If you look from 0 to 360 degrees, there's only 1/3 of those kind of sectors is really free sector. 2/3 of those sectors are wake sector. What really means is if you really use the free sector, is effectively filter out, 2/3 of your data, right? And so that is a lot of data being removed and for the quantification purpose, right? So if we summarize the IEC's action or recommendation, number one, we have to give credit to the IEC recommendation as a non-parametric data science method, and it's pretty robust and it's very easy to use. Everyone understands the basic mechanism. You can use your own laptop to write a few lines of the code, and to do the calculation. Every engineers know how the data goes in and how the data comes out and how it's manipulated. So it's entirely transparent, right? The IEC being method primarily only consider wind speed, right? They do consider air density in a very ad hoc way. It's not very optimal, right? We did some analysis previously, was reported in my book, right? The machine learning method can account for the air density effect much more effectively than the correction formulation. The IEC method doesn't really actually make use of the wind speed. They simply just control for that, right? They said you don't really use that data, which we consider not really is not really of the good quality, right? So as a result, if you follow or someone follow IEC method to establish the power curve, they are reasonable for the free sector if you account for the wind speed alone. They are not really a good their generalization ability for the general wind condition is not good, right? Typically, when you compare the power curve produced by the IEC method versus your actual performance, you see something called underperformance, right? So on the other hand, in my book, actually, I give an analogy to say we shouldn't really blame IEC for that, right? Because IEC created this standardization. It's not really for the purpose for the wind operator to use as a predictive tools. Their purpose is really try to regularize transaction. When wind turbines manufacturer sell a wind turbine to the owner and operator, they supposed to have a set of standardized condition. They can verify the claim by the manufacturer, and then therefore they can complete the transaction, right? So that IEC basically produces those kind of things. One of the analogy I use in the book to say, if you go to buy a car, right, you're going to see a kind of fuel efficient sticker to the windshield or to the window, right? When you actually bought the car and you drive it around, and then if you really use how many fuel you're going to add to your car from time to time and divided by how many miles you drive, you never really see that kind of advertised fuel efficiency being materialized. You always find that it's smaller because the reason is very simple. The fuel efficiency was advertised that is obtained on a very standard ideal condition, right? It's a constant speed running in the lab and all these kind of things, right? For typical customer, it doesn't really matter that much. The relative sense still give us a sense of which car is more efficient in the fuel and which one is less efficient. But suppose you are a commercial trucker, right? The fuel expense is one of the major expense for you to make your living. You're not going to use whatever advertised from the from the dealership, right? You're going to do a data-driven method to get your own fuel efficiency, fuel consumptions for certain kind of task. And so that's the same thing applied here, right? IEC never really asks you to use their method for your own prediction, right? They provide that for the other purpose. It's just in the vacuum of more powerful prediction tools, and all the owners or operator to say, let's just use the IEC method, okay? So people actually realize that this is not really a new story, right? I remember more than 10 years ago, I was talking to the wind industries. They were like, okay, that's an interesting angle to talk about that, right? There was actually so-called power curve working group and formed by more or less the owner or operators and some people from the national lab, both in the US and from the Europe. And they also realize this type of things. They try to say, advocate the use of machine learning method to incorporate more input variables and also use more powerful method to do the power curve modeling. So over the 10 plus years, right now, it's not really anything surprising anymore, right? People commonly accept in this era of AI, they understand the power of those kind of data-driven things. And in the package we produce, we use one set of data. This is not really, if you repeat this one on the other set of data, you probably see the ranking is a little bit different. But the binning, the last column, the binning is almost always the worst the performance, right? So we compare it with a bunch of different machine learning methods from AMK is a kernel method, and KNN, one form of deep learning, smoothing spline, polar vector machine, the tree method, and so forth, right? So over the time, actually, you can see people by using the machine learning method, they improve the number in here is the prediction error, right? They improve the prediction error by a huge amount, right? Reduce from 12% to 8%. That's about 50% reduction. That's pretty significant, right? The AMK method we published in 2015. This is one of the very first paper we published on this topic, right? The paper actually was the first version was completed in 2012. It takes quite a long time for the paper eventually to be published. It's kernel method, right? The kernel method has this issue of scalability, right? If you have all these variables in the kernel function, and they usually handle low dimension, 2-3 dimension fine, but they don't really handle the high dimension very well. But you also want to have the high dimension because there's an interaction between them, right? So you have two kind of conflicting objective. One thing you want to have the interaction, another way you want to make sure your model is scalable. So eventually we come up with this additive multiplicative model structure, which is really advised by the very simple power production law, right? That we said, from that power production law, the wind speed, wind direction, and air density are very important. So we keep the wind speed, wind direction, and added other variables as the additive element. So this way is a better balance between the scalability and the capture of the interaction. And this model also not only produce a point estimate or point prediction, it also gives you the uncertainty. So like the figure illustrated here, right? If you give a wind speed, not only you can predict the on average, what is the best prediction for that particular wind speed, but also give this distribution characterization. This is conditional on x equals 7.5 meters per second, and the prediction probability density distribution of the power of y. Okay. Now, when we're doing this type of things, it didn't take very long for us to realize one of the, I would say, rather fundamental machine learning issues, right? I'm teaching a machine learning class right now, and obviously in most of the machine learning models, and people commonly assume that epsilon, which is noise, is IID, is identically independently distributed. But we are dealing with this time series data from a physical system, right? And the data in most of the wind industry, they are arranged every 10 minutes. the original data probably was collected with even higher frequency. But here, the data is arranged at 10 minutes. That's the industry standard way. Even 10 minutes, the data actually are auto-correlated, right? You don't really expect, after 10 minutes, it has nothing to do with the data you collected from the previous stage. And by using the autocorrelation, and eventually we realized, by using the data with the core autocorrelation, we eventually realized if you do the model selection based on the regular cross-validation, it tends to select the overfitting model. And the reason is the autocorrelation will create some artifact in your pattern of your data. And that pattern doesn't really necessarily genuine, right? It's an artifact. And but your model doesn't really know it's going to fit those kind of patterns. So one of the examples illustrating here is on the right-hand side is really RID noise being imposed on a second order polynomial line. And if this is the data, your machine learning model actually can do the recovery of that line pretty well. And not exactly the line, but more or less follow the trend. But if when the data has an autocorrelation, and the data itself actually shows a more complicated pattern than the data with RID noise. And from that pattern, it cannot really blame the machine learning model, basically just want to follow that pattern, and which increase the complexity of the fitted curve, right? So we handle this question, we actually learn about this question the hard way, a little bit kind of humiliating to ourselves. I will explain that story. But it takes us a couple of years. Eventually, I think we have a solution for that. But before I tell you that story of how do we learn this problem, or we kind of deeply appreciate the problem, I want to articulate what we do here is, when I explain this problem to someone else, and they usually say, you're probably overfitting because you are doing the training error. You don't really use the holdout data to assess the actual sample error. We are not making that kind of low-grade mistakes. We are assessing the actual sample errors. But here I want to introduce this concept, in-temporal test error versus out-of-temporal test error. They actually give you something different, right? The in-temporal is like if you do the randomized cross-validation, the data, the testing data and the training data basically come from the same time period, and they maintain more or less the same kind of autocorrelation structure, because the test data is come from the neighborhood. The training is entirely use the training data, doesn't really touch the test data at all, but the testing data is being used to do this evaluation. Another set of the out-sample test error is really there's no physical overlap between these two time periods, right? The training data is used, for example, previous year, the test data is this year's data. Okay, and that does make a difference, right? So here, this slide explains how do we come to realize there's something we didn't really look into in our initial model. We published that 2015 paper. It's around like 2017-ish. One of the winning industry company asked us to do a blind test with them. It's like a verification test, if you will, right? So what they give us is 2015 data. It's a whole year data. They ask us to produce whatever the power curve for them. And then they're going to use the first half a year of the 2016 data, right? They also give us the 2016 data as X. They ask us to use what our power curve model to produce for the X and produce the Y. And they withhold the true Y. And therefore, once we give them the Y hat, they can compare with the true Y, and then you can easily calculate the RMSE or MAE, whatever you want to, right? They also use their own binning method, and which is not really different from our binning method. It cannot be different. It's a very simple method. Everyone does that more or less the same, and calculate the same Y, right? So we tried the multiple method, and when we do the 5-fold cross-validation using the 2015 data, we find our method really kind of dramatically improve the binning method. And when they showed us how we do relative with the binning method using the test data in 2016, none of our method actually outperform binning method, right? It's just like the AMK is like very close. The BART is a Bayesian tree. The KNN actually is 15% worse. Here, the minus is good. The plus is bad. Okay, the plus meaning your error is higher. Okay, and it was like we didn't really expect this to happen, right? And then we kind of think about that. We realized the problem is with the autocorrelation. So we actually had a solution more or less around 2020 when we tried to publish the work. We come to realize there's someone else actually beat us to have a more kind of fundamental explanation of why this happened. I see Alan raise your hand, and go ahead.
Professor Ding, one question about the data sets from the previous slide. Maybe it wasn't, I missed that detail, but how is the data collected? Is it using a simulator? Or
no, this is from
how is
actual
the
wind turbine. They're all physical data, yeah.
And
So
does it
it's
take
just
like
one same turbine. They collected the 2-year data, right? They give us the first year both of the X and Y. And then they give us the second year X, ask us to produce the Y hat for them. Yeah.
I
The
see,
same
I
as
see.
they give us. Yeah.
And they can measure all these environmental covariates
Yeah.
through
And
that measurement process.
on wind farm, on the wind turbine, they usually only measure wind direction and wind speed. But usually they have a met tower. On the met tower, they measure other things. They measure wind speed at a multiple height. They measure the high speed, wind speed. They can calculate the turbulence. They measure the temperature, pressure. They can calculate air density and so forth. They can measure humidity. And there's a number of these variables they can measure. Yeah.
And since
So
it's
all this
since it's temporal for a year, I suppose the data set must be really big, like
no, if
in
you think
gigabytes
about the
or
10 minutes, for 10 minutes, one data point is really about the 52,000 data point for one turbine. So for one turbine, it's not that many, right? 10 minutes, so every hour is 6 data point, and every day is 144 data point, and then you multiply 350, 65, it's about 52,000 data points.
I see.
Yeah, it's not that large. If you have 1 hertz data, you need to multiply that 50,000 with another 600. It's a 3 million data point. Yeah.
Thank you.
Okay. So when we had that our method, and we realized there's another paper is accepted to JASA, and they provide a pretty nice explanation of why this autocorrelation type of things will cause your problem, right? So we eventually our solution method is still different from theirs, so we published the solution method, but we didn't really just hang up on that particular reason anymore, because they basically provide even a nicer explanation. So they use a very simple linear mixed model. They have a fixed effect, they have a random effect, they have the IID noise. If you combine the random effect with the IID noise, basically you have a noise which is not IID anymore, right? So here in our model, our first one is nonlinear, it's non-parametric nonlinear term, but that's not really that critical, right? You have the critical thing is the noise is not IID. And then they said, suppose you have a linear predictor. In our case, not all the predictor is linear predictor, but that's also is kind of a detail you don't have to be very much concerned with at this moment. By using a linear predictor, you are able to explain these things more nicely. So through a very detailed derivation, they eventually come up with a kind of a conclusion. They said the CV, the cross-validation error, and for model with a data with an autocorrelation, is going to be this test error estimated by regular cross-validation, add additional extra term. Okay, the extra term looks pretty complicated to you, but really they have additional 2 terms. The first term is the correlation among Y, and the second term is the correlation between the training and test data. Okay, and that's how it makes the difference, right? Because if you think about it, for the intemporal test error part, the training and the testing data, they are still kind of in the neighborhood, so they have correlation, and that correlation more or less is the same as the correlation of Y itself. So you can consider the first term, I mean, in the top expression is the second term, first term in the bracket, and the second term in the bracket. They are more or less cancel each other. So if you do the in-temporal test error, you actually can use the regular cross-validation just as is. And it's going to produce the same thing if you use the more fancy correction one. The CVC, that small c, meaning the cross-validation correction. But if you do the next year, it's going to be a very different story. Number one, the Y trend, the Y test, given this large time, separate them together, and that part is going to be virtually zero, except for a few data points, really neighborhood with each other, when you cross the year, right? So whatever the things are, as long as you have a physically time series going along the line, and only on a separation line, a few data, they are autocorrelated. And after that, after like a day or 2 days, the data, majority of data in the training, majority in the data of the testing, the second term is zero. You only have the first part left. So in order to use this CV correction to choose the right model, you need to estimate the second term, which turns out is not very easy to estimate. Right? I don't think I have much time today to explain that, why that is not very easy to estimate. But that is more than people are thinking how to just do the autocorrelation of the Y to estimate that. That's not really a good estimate. And because of that, this formulation explains the problem very well, but it doesn't really say how exactly you're going to select the right model, right? So we actually end up with a very simple solution for that. We said you just thin your data to forcefully get rid of the autocorrelation, right? But the thinning of the data has a consequence. The thinning of data basically said you're going to have much fewer data, right? The thinning data is like you don't really use the data 1 followed by data 2. You use the data 1 followed by data 100. And then because data 1 and data 100, there's a very large time gap in between. So the data 1 and data 100 is not autocorrelated anymore, okay? So therefore, you can use this subset of data, which is manually get rid of the autocorrelation to estimate the model and without a problem. But you don't really want to only use 1% of your data, right? If you use only one data, 101 and 201, you only use 1% of the data. So what are you going to do? What we propose is you simply just rearrange the data. You have 100 these kind of blocks, and you use each block to generate a likelihood function, multiply them all together. It's not likelihood function anymore. It's a pseudo likelihood function. But that allows you to estimate the parameter in the Gaussian process model, and we call it TempGP. And use this one to estimate fx part, because this is considered as kind of time invariant aspect. And then use the difference between the y minus fx to estimate the GT, which is local autocorrelation part. And then you add them together to generate this model, okay? And I'm sorry, this is and when we do, also there's questions that, how far away you're going to downsample your data, right? And there's a very simple formula you can use to calculate this t to allow you to adjust for each different kind of data set. And we'll apply this one back to that 2015, 2016 case. And we find not only they reduce the error for the 5-fold cross-validation, but also, on the testing error part, it's a negative. It's not really a big negative, but nevertheless, it's negative, right? The other method without necessarily account for this autocorrelation is all positive. In this particular case, it's hard to beat their baseline method. There's another reason, is because they clean the data is already very well. They give the data to us is already pre-clean. It's not 50,000 data points. It's roughly about 2/3 of that data. And so it's not really hard for the binning method to actually do a good job to capture that trend, okay? So we were able to beat the binning method in this particular case. It's not easy. And the Gaussian process model is pretty expensive to run. And the original version takes an hour to run. So recently, my PhD student and together with our statistical collaborator and use a Vacuum approximation, be able to speed it up to just a couple of minutes for 1 year worth of data. And the accuracy deterioration is only about 1%, right? So if we use the TempGP as a reference, the TempGP the last row should be 1 because it's itself, right? The faster version of TempGP is only 1.01, it's increased by 1%, okay? The TempGP was able to reduce the RMSE fitting, the model fitting from binning method by nearly 80%. So that's a pretty significant reduction of the model prediction capability. I think I'm going to, right now it's exactly 4 o'clock. I'm going to stop here and take 5 minutes of break. And just in case anyone else has a question, we can have a little bit kind of discussion before we proceed. What do you think, Alan?
Yeah, I think sounds like a good plan. Just one a small announcement is that I left the registration form on the chat, so if you can register, so we can provide you with the material, the recording, and also a certificate of attendance of the tutorial. So yeah, if there are any questions for Professor Ding.
Yiding, when you calculate the power, you don't consider the wind direction in the formulation, in the formula. My question is, in the wind turbine, they have a pitch roll control. So basically, depending on the speed of the wind speed, you mentioned too high, too low, they may adjust the direction of the wind, the turbine blades. So in this way, there is the power generated may not be directly related with the wind speed because the direction, the turbine blades react to the wind speed. So how to explain this?
So you're talking about this equation, right?
Right. In this equation, you have wind speed, but this wind speed does not consider the controller capabilities to adjust the wind turbine.
Right. So this formula doesn't have explicit wind direction. So, but it has an attack angle, which is a function of CP. Or should I say, the CP is a function of attack angle. The attack angle is the relative direction of the wind speed versus the blade. So that's an attack angle. For example, you have an airplane kind of take off, right? The wind is coming here. So the relative angle between these two is the wind speed. So the wind speed play a role, right? In the wind turbine control, they have the yaw control. The pitch control doesn't really affect that wind direction much. The yaw control is really help the wind turbine try to point to where the wind come from. But the yaw control cannot be exercised too fast because the wind nacelle is the wind turbine nacelle is very heavy. So they only can change the direction slowly. And therefore, when the wind actually changes suddenly, there's always kind of sluggish. There's a delay in terms of readjusting the wind direction. This formula is really assume the wind is directly hitting on the wind turbine on the free stream type of things. So this formula is technically correct, but the reason they don't really always produce the wind power data exactly reflecting this formula is because of that complexity. Now, in the machine learning method, we can use the wind speed, wind direction, and as the input variables. The question is how you're going to learn that, right? What is the best way for you to learn that? There's an additional complexity to that. It's like currently all the wind speed and the wind direction are point measurement, right? If you look at here, they are measured on the anemometer and the vane on the end of that nacelle. It's one single point, but the entire wind blade is pretty large. So the wind is really kind of as spatial blocks hitting the wind blade. There's the speed is not really uniform everywhere. So sometimes people to use, for example, wind shear, so which is the gradient of the wind speed, try to capture that effect. And so far, there's still a kind of ongoing issues to say what is the best way to able to take the multiple wind speed measurement and to make the wind power model even more accurate. Yeah.
Okay, thank you.
I have a couple of questions about your this temp GP model. So the baseline is the binning method, and we know the binning method has this curse of dimensionality issue. So I was wondering like what environmental variables are used in bidding and how the industry handles this multivariate input case. And second question is how you handle the wake effects. This one is just for single turbine, or this is from the power of entire farm, or like it.
So
So
this
it's
one is only a single turbine.
single
They
turbine.
only provide us a single turbine. We don't really get to choose what kind of data we use. I don't remember. I think the input variable is probably 4 or 5 for this particular things. For binning, they simply just use one wind speed.
Oh,
They
they
don't
just
use
use wind speed.
Yeah, they just use one wind speed. So the story is like if you still cannot beat binning, why we need to use your method, right? This is why it's like when we present this one to them, it's like they don't talk to us anymore.
I see.
Right. So that's the humiliation I was talking about.
So before you try this, develop this new way of cross validation considering temporal correlation. So here in this figure, you have this f function, and this f function doesn't consider any correlation, right? It's just you use external variables and fit GP model, SVM model, so on and so forth, and you assume epsilon is IID.
Yeah, that's right.
So simply,
and then you're going to choose.
So simply,
you're not
can
going
we
to use
apply...
all the 4 variables, right? 4, 5
right,
variables.
Right.
So you're going to choose which the wind speed must be one of them, right?
Sure.
So suppose I use AMK, only use wind speed. We're probably going to outperform binning slightly. At least we don't really necessarily be 4% worse, right? So, but when you use AMK on the 2015 data, by using cross-validation, choose which variable to use. I typically choose 1 or 2 additional. So eventually, my AMK model has 3 inputs, and the binning only has 1 input. And since that 1 input one is more robust with the use on 2016 data, right?
Okay.
This is exactly the definition of overfitting.
Yeah. My next question is simply, so here the f function, you use AMK, SVM, KNN, and you assume IID in the noise part, right?
Yeah, so not only we assume, if you look at the element of statistical learning, it's assumed throughout.
So can you apply autoregressive model to epsilon? So we fit we have estimated f, and then we have residual. Then we can apply autoregressive model to the residual. So then we can that can be some just simple approach to the auto calculation.
No, not simple approch. Not necessarily simple approach. There was a paper. There's approach, but it's not necessarily a simple approach. That approach is called pre-whitening. So in 2003, someone published a paper in JASA. So exactly follow what you just said, right? They first fit the model, they take the residual is autocorrelated. They try to white this, they do a kind of some kind of analysis to make the noise to become IID noise, right? And then they do a bunch of other things, and then eventually back propagate and then to get to the original model, right? This approach is called pre-whitening. So in our TimeGP paper, we actually compared our approach, this thinning approach, with the CVC, right? If you try to use CVC as best you can do to estimate the model order, and compare with, they're also in computer science, they do time split cross validation. So here I didn't really talk about that, right? What they do is like you don't really do the randomized cross validation. You do a time split. You do one time. You only use distance time to do the cross validation on my current time. That way you don't really have this kind of contamination issue, right? And then this pre-whitening paper published in 2003, we compare with all 3 approach, and it looks like they have their pros and cons, and there's certain aspect. It looks like the thinning is still. Once I joined the Georgia Tech, I find the Roshan Joseph's twin GP is actually a very good method too. They don't really exactly handle the directly handle the temporal correlation issue, but because of the mechanism they use, they can alleviate the impact. So in this new paper we published recently, right? Not a co-author with him. So this is a new paper. It's more or less on the computation aspect. We actually compared with the TwinGP. So TwinGP in some cases on the autocorrelation, they can become very, very bad. But in some cases, they perform very, very well. They are not really affected much.
In terms of efficiency?
No, yeah, in terms of the effectiveness.
Effectiveness.
In terms of how much
prediction.
they can, fit the model without overfitting. So I talked to Roshan, and he couldn't really explain exactly why it happened now. It just so happened. And one of the good things about TwinGP is it's very fast. It's faster than the type of things we eventually proposed here. Yeah. So it's probably the fastest GP method I ever used. So I highly recommend if you want to use something, you want to use a fast method to produce something useful, TwinGP probably is the way to go.
And it can handle high dimensional input?
I believe so. Yeah, there's no particular limitation of how many inputs they can handle. Yeah.
So then the pre-whitening, what is the performance of pre-whitening compared to the binning when you evaluate with 2016 data?
We didn't really evaluate it. In the TimeGP, we basically just compared this different approach with the TimeGP, right? We use the TimeGP as 1, right? If the same result is 1, if it's better, it's below 1. It's otherwise it's so I don't remember exactly the quantitative comparison. You can take a look at the paper. Yeah.
I see.
Okay, probably I can continue. Actually, we had a more than 5 minutes break. Okay, so that basically answers the first part of the question, right? It started with a simple question, but afterwards through the engineering problems, make us aware of some of the unique problems over there, right? The second question about the causal inference and what kind of subset to use. This one actually is the problem we try to answer. The causal inference also try to answer. They usually try to answer two big questions. One is to determine which variable, which factor has a genuine cause and effect relationship with the response. Another one is quantify that effect, right? For our type of a problem, the first question is not really that much interest because we deal with a physical system. So the physical law basically said the wind produces power, not the other way around. So we don't really need it. For us, it's more important to say, other than wind, so there's no question the wind is driving the power. Other than wind, in this particular settings, is there anything else we need to include in the model, right? So that quantify the effect of the response is more important, right? In here, we actually invoke Don Rubin's correlated matching method, which he published more than 50 years ago, which is still relevant in this type of setting. Causal inference is not really used that much by engineering systems. It's really because for most of the engineering system, it's pretty easy to do a physical experiment, the controlled so-called CRT, right? Controlled randomized experiment or test. And so you don't really need to use a causal inference. Now, the wind application actually present one of the situation, an engineering system produce actually a set of natural experiment. You can observe, but you cannot control, right? If you do this you do this upgrade, right? You know at what time you did the upgrade, before and after, and you can collect the data before and after, and then do a comparison. And the question is how you can make the comparison and to get rid of the so-called confounding effect. And the Rubin's idea, the 50 years and strong. And he said you need to carefully select the data point for making the environmental condition probabilistically comparable. Okay, it's not really deterministically comparable, but probabilistically comparable. So here give you a sense of this we use the two turbines. One is called test turbine, another control turbine. And before the matching, you can see some of the environmental condition confounding the effect of the turbine grade, right? This is data collected on the control turbine, which there's no upgrade. So technically speaking, before and after, if all the environmental condition is the same, the power curve distribution should be the same. If you look at this curve on the bottom right corner, the dashed line is from after the upgrade period, and before the black one is the before upgrade period. They are not the same, right, Alan?
Professor Dean, can you share the slides in your screen, please? I think we
I'm
cannot
not
see
sharing the slides. I'm sorry. Yeah.
Yeah.
No, sharing. I'm reading the slides.
Oh.
I see the
yeah.
slides.
Yeah. It's me. It's my Zoom. Thank you.
Okay. All right. Let me go back to. Let me stop sharing. I don't know where am I, so I will share.
You ready stuff now?
Because I get out of that mode and I couldn't really go back to that. Okay. So now you see, right, Alan? Okay. So here you can see the control turbines. They don't really produce the same type of energy profile, and primarily because of the wind speed, the temperature, they are all different, right? The wind direction actually match with each other reasonably well. So the idea is really, can you select a subset of data which you make the input variables more or less the same, like in the probabilistic sense, right? If they form a distribution, the wind speed, wind direction, air density, they're more kind of comparable. Once that happened, and what happened to the control turbine power? And it looks like they also matched with each other reasonably well. And this kind of, to give us this feeling, once you do this type of things, you can eliminate this kind of confounding effect, which is not really part of the turbine. This is really kind of an external factor, right? So we come up with a specific techniques, follow the general idea Don Rubin published in 1973, and to do pretty much the same thing, to do the currents matching. So here, give you the example to say, here is the wind speed, here is the temperature. For this particular example, there's no air pressure measurement, so we cannot calculate the air density. So, but the temperature is good enough. And once we match the before and after period of the for the turbine upgrade, and we still see the before and after the power production, this delta energy is really attribute to the turbine's innate change and than anything else. So this is the second part of the how to select the subset of data. Now, when we're doing this kind of things, we find the selection, because all this kind of power probability density curve cannot be controlled very precise. There's still small difference in here and there. They generate some kind of bias. So when I was still at Texas A&M, I talked to my statistical colleagues and to say, how we can further reduce this kind of bias. The bias is not large. It's about 1 to 3%. But that's exactly the type of amount, people try to detect in the upgrade effect, right? So even it's a small in the absolute sense, but it's pretty large in the relative sense. And one of my colleagues specialized in causal inference and, suggest a number of improvement to make it more accurate. We tried all of them, and none of them works. And we still don't really know why, what is the best way to do that. So I suppose this is still an open question, it's for anyone is interested, we share some of the data, so you are more than welcome to try your own hand to see if you can make these things, the bias be further reduced, okay? And the last part is we need to quantify, right? And here, because we use a Gaussian process model and make the quantification is relatively easy to do. Now here we needed to do is really kind of quantify two power curve, two functional curve. And in order to quantify this two functional curve, we also want to do a so-called local test instead of a global test. By global test, what I mean is you really give a binary response to say curve 1 is different from curve 2. By local test, we want to identify the region between these two functions. They are statistically different, right? We want to accumulate that difference, which we can advise certain kind of decision making, but also from engineering point of view, for the entire wind spectrum, which direction, which region, which wind region the difference appears is very important for the design engineer, because that is something their theory will say, once you put my VG on, this part of the performance is going to be different. So you can, if you have the data, you can verify that claim is true or not, right? So when we look at the literature, there's not really that many works really work on the so-called local test on non-parametric function. And there's an issue about also what kind of data you're going to use, right? There's an input alignment issue. If you have the power 1, the curve 1, curve 2, they come from different two data sets. Are these two data set point, they are aligned with each other? They're basically the same, or they are not the same. In our case, the two input data sets, they are not guaranteed to be the same, okay? And also, do you have replication, right? For any kind of wind speed, do you measure multiple power for that given wind speed and other environmental condition? And in our case, there's no replication. For every input condition, there's only one measurement. And the closest work to our work is really Cox and Lee published in 2008 in Biometrica. And the difference is really, they require the data with replication and they use the data from the same input location. It's a perfectly aligned input. And they identify the region, but they didn't really quantify. Their test is a local test, but they didn't quantify, right? But they use a permutation test. So they are kind of a distribution-free type of test. In our case, we assume that the Gaussian distribution, which allow us to do a little bit further. Of course, we assume it's a Gaussian distribution, and that if you accept that kind of assumption, and the result is reasonably good, right? So here is a little bit kind of, I think that right now the audience is all very familiar with the Gaussian distribution setup. This is a hypothesis test with a Gaussian process prior, and then eventually we going to construct this probability region, we call the confidence band, and with 1 minus alpha confidence levels set. All these things, the first 4 bullets are more or less standard. And but when we're doing that, we run into one of the computational problems. So eventually, and this is exactly one of the points my colleague, former colleague, Retool, gave a lot of help to suggest to use the KL expansion to eliminate, to get rid of that computational problems. Okay, so here is the result, right? If you look at the one of the case, really the null hypothesis cannot be rejected. You find that the difference between what F1 hat minus F2 hat is a curve. This is the blue line is the difference of the two curves, and they are more or less within this 95% confidence band. Okay, and because that happened, and we said F1 equal to F2. And in another case, the blue curve is the difference band. One portion of that is greatly outside the confidence, 95% confidence band. The blue area, blue shaded area, is what we call the statistical difference, right? And if we want to accumulate that difference, that's the difference we're going to add together, from time to time. And this particular area is also important. If you remember, we said previously that the rated wind power is about 12 meters per second, right? It's right in the middle of that part. And that area right before that rated power is the power curve increase most the steep part, and which if you change that steep, that will give you the maximum benefit of modifying the power curve function. So this more or less confirm whatever they did on that turbine really kind of deliver on the promise they intend to do. Okay, right before the COVID, we actually had a collaboration with a Goldwyn company. They are very interested in the type of things we did with the power curve analysis and also the wind turbine evaluation, performance evaluation. So they give us a multiple year of data from 2015 all the way to 2019. And in the whole period, they did a multiple upgrade. They didn't really tell us what kind of upgrade. They don't want to tell us the upgrade. They give us a code name, right? The first one they do is the baseline is a V0. And then without changing the V0, they add something is a P1, okay? And then without changing the V0 P1, they add something as a V1. And then they add another one is P2. And so you basically have three, this kind of change point. The change point is already known. They want to ask us is how much this P1, V1, P2 action will change the turbine performance, right? Later on, they tell us it's all about the software control logic type of change. There's no hardware change. And when we use our package to calculate all the things, and we find that if we, without quantify the statistic difference, without fill out the noise, you see the result on your left-hand side. And by only accumulate the statistical difference, significant difference, you see the result on your right-hand side, right? The right-hand side basically said, you know, on average, the P1 and the P2, they don't really change much, right? In specific turbines, they probably will produce a difference. This is of the wind farm of 66 wind turbines. But the V1 actually has quite a significant, right? The box, which is 25% quantile and to 75% quantile, is way above the zero line, right? This thick line, which we see in the middle of the plot, right? And so that is a pleasant surprise to them. We were planning to continue this line of collaboration, and when the COVID happened, and also the relationship between China and the US getting very complicated. So right now, this you know, that basically is a conclude of our collaboration with that particular project. We also did a simulation study because for all this quantification use real data, it's very hard for you to say, are you really sure you recover the number accurately, right? Because we don't know the underlying truth. So one of the way we can have some kind of sanity check is suppose we simulate some data, right? This is not entirely simulation. We basically take one set of data, control turbines data, real data, you know, from both of the X and Y, the power. And now we take a nearby turbine, the test turbine, the same X, different Y, right? And then we, in this particular case, the control turbine and the test turbine, none of them really go through any kind of upgrade. So even we call the other turbines the test turbine, is actually just for the naming purpose only. And we select a time point as the presumed time of upgrade, and then apply a certain percentage increase of the power to the test turbine, but only for the wind speed greater than 9 meters per second. And the reason for that is it's not really a constant anymore, right? Or at least you don't really know exactly what the constant unless you do a calculation. And the reason we apply it to the wind speed greater than 9 meters per second is also advised by one of the wind company did this analysis with us, because they're concerned about this 9 meters per second is just a few above, you know, few meters per second above that 12 meters per second rated power. They believe that is most important region, right? They said, if I did something, I usually will improve the power production about the 9 meters per second. So just to simulate in that sense. So by applying this one, we actually know what is the constant improvement we applied. And then we can calculate all the data after apply this improvement, and then to say what is the effective, because there are certain data point has not been multiplied this constant. So if you add all the things together, compare with the baseline, you will calculate something we call R prime, which is the effective, the percentage improvement for that particular data set, right? So we run this analysis from 2% all the way to 9%. and the effective R prime is 1.25% to 5%. As you can understand, usually for the small percentage, it's harder to detect, right? We have multiple options of try to recover this constant, the R prime, and the ratio close to 1, the better, right? And the one we eventually implemented in the package, which also published in the paper in 2021, was able to consistently recover this constant within 10% of the underlying truth, right? The simulated truth, right? We also did some of the field analysis. Actually, the very first one, even though in the 2015 we had a accumulation with one of the wind company, but in the 2014 we did something good. In 2014, the very first analysis with the EDP North America, they asked us to do a blind study with them. And in a blind study, they gave us a 3 turbine data. And they said, we tell you this particular date. If anything happened, it happened on that date. So you can use that data as a kind of a demarcation mark, right? The before and after. They didn't really tell us how many turbine has been modified, apply this retrofit. Of course, they didn't really say which turbine is being modified. So we have 4 choices, right? There's 0, 1, 2, 3. There is still a choice because even they said some turbine probably being modified, it could be 0, right? There's no turbine being modified. So we applied our analysis and eventually we identified one single turbine. We said that turbine has been given this VG installation, the other 2 turbine has not been given the VG installation. And turns out we identified the right turbine, okay? And so that actually really kind of improved our credibility with the EDP North America. And one of the reasons they want to do the blind study, especially for 10 years ago, is very simple, right? They don't really know that much about all this kind of data manipulation we did in the background. And so they don't really know if we really have this analysis to see this kind of effect, or we just want to produce a narrative which is satisfies it, right? So they want to, even they don't really know the underlying truth, at least they know in this particular case which turbine has been upgraded. So they want to know, did we overfit that data so much and we couldn't really know what is going on here, right? So at this moment, at that particular aspect, I think we were able to do a good job convincing them we are not really overfitting that data, okay? And afterwards, we did something else. The first 3 analyses all related to VG installation. And the 2020, 2019, 2020, we did this analysis. We reported in the previous slides of the evaluation software and the control logic. And the 2021, 2020, 2021, we did an analysis about the leading edge protection with the Wind Energy Institute of Canada. And most of the work is published. They allow us to publish the result to the conference and the journals. So this is our package, right? For this R package, if you this is really the cover. We have a very simple help document, but you can click on this one. It brings you to this R document, which there's a bunch of questions. This is one of the questions give you the case study. You guys can see my PDF file here on the screen, right?
Yes.
Okay, good. So here give you step by step, right? The first step, where to get the data, right? There's the turbine upgrade data released together with the book's publication. And then for you to download, there's 2 sets of data. One is for the VG installation, another is for the PJ angle adjustment, right? And this is in R, right? In the R environment for specific the syntax, right? The command line you're going to use to load the data, load the package, and then specific line to use that particular command line in the package, right? What are you going to use and so forth, and eventually they give you the calculation. In this particular one, it's R equal to 2%, R prime 1.25%, and the R estimate 1.12%. The R ratio, R prime ratio is 0.9. The 90% range is about 10% of the error, right? And then the next one is to try to do the VG upgrade. So if you are interested in this type of things, I encourage you to just follow this link and follow this use case example. And I suppose that give you a more concrete idea how we did this analysis. Okay, so let me see. This I have a little bit more time just to give I basically finished about the power performance analysis, but there's some other things we did either before and after some ongoing work related to the power curve modeling issues. I thought it's of interest to the audience, so I'm going to present here. But before I go forward, any questions on the turbine performance analysis part? Okay, so 3 other topics and roughly about the 4 slides per topic. And one is a shape constraint machine learning things and sign constraint machine learning, and also a spatial temporal data on the incomplete partially observed grid. Right, so one of the subdiscipline within industrial engineering is called production economics analysis, PEA, right? And the basic idea of the production economic analysis is try to establish this kind of things called the efficient frontier. The method used to establish the efficient frontier is called the DEA, data envelope analysis, okay? And the idea is a simple, right? So suppose you have different kind of firms or companies, right? They use a different amount of input, they have different kind of amount of output. If you put this on the 2-dimensional curve, you will find the company D is not very efficient, because if you compare with the same input, the company E use the same input but produce more, right? If you look at the same output, the company F produce less, but they also use produce the same. I'm sorry, the company F produce the same, but they use less input. So anything on this efficient frontier is more efficient on the data point inside that frontier. That's why the line is called efficient frontier. But it's hard to compare F and E directly, because the F produce less, but they also use less. So when the economists establish the efficient frontier, they usually have a few of the requirements. One is the monotonicity, right? It's kind of increase. Another is convexity, right? They consider this efficient frontier to be a concave curve. Now, when we look at the general concept can be applied to the wind turbine as well. Wind turbine considers a power generation unit. But the power curve is not really entirely concave. It actually has 2 parts. One part is convex, another part is concave. They connect at the inflection point, but nobody really knows exactly where the inflection point is going to be, right? And also it's a stochastic, so the observation is not really noise-free, it's noisy. On the plot on top, this the DEA type of setting is deterministic. In many of the company settings, the output is really the revenue, which is in dollars, right? Not supposed to be deterministic. When you observe that, there's not really much noise. You're not supposed to tell me I made $1.5 million. Actually, there's an epsilon being added to that, okay? But in this wind turbine data, because it's measured use sensor, so there are always random noise into that. But the idea is still there, right? Suppose you can establish this kind of average performance, which is a blue line, and then you can quantify the systematic inefficiency of these particular turbines, and then you have this red line, which the gap really kind of help you to quantify the systematic efficiency, right? So what you need to do is you need to modify your model a little bit here. So the model has some kind of similarity to this early model we have, but here we actually assume the epsilon is IID. So if you need to get rid of that autocorrelation, this model needs to be F minus mu plus G plus epsilon, okay? And so here the U is the systematic inefficiency. The F is the efficiency frontier. So the F is not exactly the same F as we used before, because the previous F is the average power curve, right? Here the F is the average power curve out of the systematic efficiency. How to estimate the systematic efficiency actually is a complicated issue. So I don't going to get into that issue here. But suppose you trust me, we actually can estimate that systematic efficiency, and then we can generate this kind of frontier function, and then use the average power curve and the production efficient frontier function. We can calculate this theta coefficient, which defines the productive efficiency, right? So when we apply these ideas to the wind turbines, this is real data. It's both of the onshore and offshore 4 different kind of turbines in the 4 first years. And then initially, when I looked at the result, I suspect my PhD student did something wrong, right? Because if you look at the first, almost all the turbines, the first 2 is like the efficiency increased for the first year, right? And even for the second year. And for the next 2 turbines, the efficiency increased all the 4 years. And then this is around the time we come across this 2014 papers I referred to at the very beginning of my tutorial. Is he said that he didn't really do anything wrong, and he come up with this paper said this is the real field data, and they analyzed. If you look at the first 2 years, they also find this is for the whole wind farm, right? They also find this kind of increase. So we believe that's probably the burning effect for the wind turbines. They have this kind of, initially the efficiency is increased before they start kind of decreasing, okay? For the, this is the reason we said is shape constraint is because of the power production curve is required to be convex followed by concave. So in order to impose that kind of shape constraint to analyze that or estimate that the mu term, and we have to impose the constraint function do the machine learning before doing the machine learning. Okay, and for the sign constraint machine learning, we apply that to the wake effect analysis. This is only one pair of the turbine. It's not for the whole farm. So it's only one pair of the turbine, right? If you look at the data, this is also the real data. We take the difference between Y1 and Y2. If Y1 and Y2 equal to 0, you have that kind of green line in the middle, right? So Y1 greater than Y2, you have part of the data is going above the 0 and then going below the 0. So this pattern for the above 0 and the below 0 part, significant above and below 0 part, is really indicate that wake sector, right? And the depth of that is we call it wake depth, and how much you in the wake sector. If you write on the line of the wake effect, you're going to have pretty significant the wake depth, and then also the wake width is related to how wide the cone is going to be. Okay, so we want to use the data-driven method to estimate this the wake characteristic and also estimate the overall wake loss related to the AEP relative to the AEP, right? So we established 2 models, right? One is for turbine 1, another for turbine 2, and we assume there's a systematic inherent inefficiency eta 1 and eta 2. Suppose these are of the same turbine, and their frontier function fx is can be assumed to be the same, but the actual production is not. So that's why the f minus theta eta 1 reflect the actual production performance of y1, right? And then the third term is really the wake effect, right? You have a wake loss, which is omega 1, omega 2. But omega 1, omega 2 is always non-negative. They only exist when one turbine is in the other turbine's wake sector, and they don't exist when it's outside the wake sector. And the wake is always reduce the power production. They don't really kind of increase the power production efficiency. Okay, so once you take the difference, you have the three terms, right? Basically two terms, because the omega 1, omega 2 is only one will exist. And then the first term is the eta tilde 1 dash 2 is really the inherent difference between the two turbines. And for the first term, there's no sign requirement because we don't really know if the turbine 1 is more efficient than turbine 2 or is the other way around. We only know the wake effect need to be non-negative, right? So we use the spline functions to try to estimate the two different terms, a cubic smoothing spline for eta and a simplet regression spline for omega 1, omega 2. Okay, and here is the field analysis. We select a wind farm with 200 plus wind turbines, and we identified 6 pair of them. When the two turbines, the distance is close enough within 5D. The D is the rotor diameter, right? Is within the 5D. So they are close enough to generate quite a significant wake effect. So the 6 pairs location in the wind farm is indicated in this way. The circle is 10D, right? 10 rotor diameter. So they have a fair amount of overlap because they are actually close. The actual location is rather close. And the table on the above indicate the estimate by using this kind of sign-constrained machine learning method, right? The pair 2 actually has quite a bit of difference, after a number of years operation of this two turbine. It's identical turbine. It was installed at the same time, but after 3 or 4 years, and there's about 3.5% difference between these two turbines. That doesn't really happen to other turbines, right? So, if our analysis is true, this can be used by the owner and operator identify, what is the reason for this particular pair, they become different more significantly over the same period of time of operation of the other pairs. The average wake loss to the pair is about 1%, 1 to 1.5%. That is very consistent with some of the other studies and other people did and over the years. Okay. The last topic I want to mention is really speak of the terrain effect, right? Because if you have a flat terrain, of course, you don't really concern much about the terrain effect. But if you have a kind of slope and other kind of complicated terrain, the wind coming into the wind turbine is going to be affected by the terrain, okay? And we know the physics knowledge tells us if you have different terrains, you're going to have a profound effect on the wind power production. But the existing power curves up to this point, including there's a type of the power curve, there's no course, okay? Including our own development, doesn't really directly incorporate the terrain, okay? One of the reasons is most of the time people don't really know the terrain, they know there's a terrain, but they don't really know the quantitative characterization of the terrain. And we are lucky, through the collaboration with Goldwind, and we actually acquired one set of the data, and which has a very detailed current characterization, right? So the set of the data we released actually has 3 characterization of the terrain: slope in terms of degrees, right? Rx, which is really ruggedness, the roughness of the terrain is dimensionless, it's really a fraction. And also the ridge is kind of increased the height and over a certain kind of range in meters. So technically speaking, a terrain incorporating power curve should be a special temporal function, right? The previous the power curve is always a special function for a turbine-specific production function. But if you want to incorporate the terrain, you have the S term, which is a spatial term. They only change with different location. They don't really change over time, okay? And when we look at this kind of spatial temporal problems, we find there's a rich literature to handle the type of spatial temporal data on the grid, but on the fully observed grid. If you look at the matrix on your left, right, that's type of things that I'm talking about, the fully observed grid. For any combination of the X and the S, you have a corresponding Y to be observed. But for the wind farm data, it's not like that, right? Because all the X's are different. So we cannot really kind of have one common set of X over that. So we have all the Y's is really kind of on a kind of incomplete grid, right? We call this one on the partially observed grid. And actually, it's many of the data point over the grid, they are missing. And they are structurally missing. They are not really randomly missing. So if you have the fully observed grid, only have here and there some missing data, it's relatively easy to be handled. They are randomly scattered over the grid, typically less than 10% of the total data point. And in our type of case, we have 98.5% of the missingness of the data, right? So what are you going to do with that? So our approach is like create something fake. We call it pseudo, right? The pseudo is sounds nicer. So we create a set of pseudo input and output, and we use this pseudo input X and together with the real S to create a pseudo output Y, right? And then we basically recover this fully observed grid. But because our X is not really the real X, the Y is not real Y, and there are some cares you need to basically take care of that, right? And we can put these things in a more complicated optimization function. I believe optimize the whole thing is pretty difficult. It's pretty daunting. So we didn't really do that since we choose a easy way out. We do a divide and conquer. We decide X first, we decide Y second, and then we estimate theta. Okay. And if you have a better way to say, I can really solve the whole optimization problem altogether. And this is really large data, right? The Professor Xu asked me the number of data points. So this is for wind farm with 66 turbines, and each turbine is 50,000 data point. So you multiply that is over 3 million data points, right? You can deal with. So it's not very easy to try to estimate the optimization function altogether. At least we didn't really find a very efficient way to do that yet. Okay. With this kind of model, it really allows us to quantify the terrain effect from this kind of data-driven method directly from the data from the turbine operation, right? So here, it turns out the Rx is very significant, and followed by the ridge, and then the slope is not so significant. Of course, we also did some of the comparison with other kind of machine learning method, like multi-layer RNN, XGBoost. We did compare with the TwinGP because Roche Joseph is a co-author of this paper. Obviously, we compare with his previous work, and the BHM is a Bayesian hierarchical model. One of my former PhD student, Abhinav, used that method, but it's more parametric power curve, so it has its own limit, right? By using that one, even use the terrain, but the performance is not so great, right? The binning actually, if you only use the binning and you just translate to a different terrain, and sometimes they do not so bad work, right? 27%, but compared with if the parametric function doesn't really exactly satisfy the assumption, the binning still can do better. Now, one of the questions, right, if you are interested in doing some of this kind of work, we're going to find the data, right? And we had that question in mind when I published that book. So we initially released the 10 data set when the book was published, and the 10 data set primarily used to generate most of the examples in that book. After that, after 2019, we released the additional 1, 2, 3, 4, 5, 6 data sets, okay, used in additional publications. And so we call it extensional data sets, and including the failure data sets, and including the terrain data sets, and so forth. Some of the data sets is pretty unique. For example, the terrain data sets, as far as I know, this is the only terrain data set is available in public. Okay, if you go somewhere else, they don't really have the terrain data set. And I serve on the organization committee for IEA Task Force 43 on wind digitalization. So one of the efforts I led over there is really try to collect all these kind of open data sources and put it in one page people can access. And so if you click on that, the link open data source catalog, you actually can find the entire set of the open data set. There are 32 data sources, and the DSWE is one of them, right? But I still believe that DSWE is pretty unique among the list because the majority of the data source, open data source, are the resource data. They only have wind. They have other environmental measurement, but they don't really have wind power production. Okay, so you have your axis, you don't have your Y. Some of the data has both of the X and Y, right? DSW is one of the data set, and but there are not that many has the both of the X and Y. So that's why I thought that the DSW is a pretty valuable resource for anyone who want to do this kind of research. Okay, and that's pretty much my tutorial, and I like to express my special thanks to former and current student still work on this kind of problems. Okay, and so that I have 5 minutes, and we can conclude here and give everyone 5 minutes back, or if you have any questions, I'd be happy to answer.
Thank you very much, Professor Ding. So are there any questions? So one question that I have is, now AI is like becoming very, very popular. So have you encountered or have you think about incorporating AI in your analysis, or whether the companies that you have collaborated with, are they also seeking for this sort of application?
Yeah, so there's a different kind of applications. I think, by AI, I suppose you mean the more kind of narrow definition of AI, right? Because everything we do here is a part of in the broader definition of AI, right?
Yeah.
Yeah. So the narrow definition, like Gen AI, back when I was at the Texas, my friend at that time was the executive vice president, the EDPR, Brian Hayes, asked me the question, how do we train a worker, right? How we assign the worker doing the scheduling things. At that time, I don't really have a much better answer to give to him, right? But I think if the Gen AI was available at that time, we could possibly to use the Gen AI to do the scheduling, to match, the worker together, and to generate a certain kind of menu and the use case and for the worker to use, right? After I left Texas, Brian Hayes also left the EDPR. He took a CEO position at another company. So I need to follow up with him to see, whether or not there's a new need and we can contribute to that particular part, right? On the other hand, we still working on research questions, right? I think we can contribute the service. I don't think for me to do this kind of Gen AI things at this level really constitute as a research, right? It's a good service to the industry, no question about that, right? Maybe that would be the first step. When you do this kind of things, you encounter some of the things of interest to our own research, we can uplift that to a high intellectual level, write a paper. That often happens to my problems, right? Because my very first problem of power curve, when the company person tell us what they use is IEC binning, and my first reaction is we can do better. Because I know a lot about the power, the machine learning things, we can do better than that. And at that time, I don't really have a feeling we can publish that somewhere else, because it's really kind of use the machine learning method to do that. But when we do that things, there's other complexity. Eventually, we publish the first paper in JASA, right? So maybe that things we needed to start from some simple things that help the company solve some problems. In that process, we also find academic intellectual problem to solve and then publish from there. So I believe there's a lot of opportunities, and I'm still seeking those opportunities.
Thank you. So any last question? All right. So Professor Ding, oh yeah, go ahead.
Oh yeah, just a simple question. So related to Alan's question, you work with several industrial partners, and I guess it's not so easy to initiate and also to maintain the collaborative relationship with industrial partners. So I would appreciate if you share your experience with us.
There's not really a formula to follow. I think I was lucky in the sense Brian Hayes was he graduated from Texas A&M, and not only that, he graduated from industrial engineering in Texas A&M. So I think that gives a kind of a very good prior, right? If we talk about in the Beijing things, since I'm on faculty in the place he graduated from, even he doesn't know me, to start with, he sort of kind of look up to, the faculty, the place that he graduated from. If it's not because of that, I think the initial collaboration is probably not as smooth with EDPR, right? But the collaboration with the EDPR is very important, right? Number one, to let me understand the real problems, the actual, their baseline, the company, what they use, what they're concerned about, all these kind of things. Once I worked with the EDPR, and I was much more comfortable to talk with other companies. And when I talked to Goldwyn, for example, and they were very surprised I'm in a field they never heard about. So, the type of the knowledge accumulated over the time, right? You understand how the turbine works and the terminology they use, the type of method they use, and my baseline is their baseline. That makes them comfortable, right? If I said, this is my baseline, they said, we don't use that baseline, and I don't want to use their baseline, and then you're going to get this kind of language problems, right? Often happen between the practitioner and so I think I was lucky in a sense, and Brian, he's eventually almost become a personal friend with me. So I need to follow up with him. Right now he's with a new company, but his new company is not a wind company anymore. His new company is a battery company, which is important too. Actually, it's a Korean subsidy company. It's a part of SK. Yeah.
SK. Oh, okay.
Yeah. It's part of SK. Yeah. He's the CEO of that company. Yeah.
All right. So, well, thank you very much, Professor Ding. And now we can wrap up. So thank you everyone for attending, for connecting. We will reach out to you with the certificate of participation as well as with the materials.
Okay. Well, thank you very much, and have a good weekend. Bye.
You too.